So we're looking at some problems out of section 4.5. We're going to look at problems 5, 6, 7, and 23. So let's look at question 5. So question 5 gives the function y equals tangent of 2x. The directions say that they want us to describe the graph of the function in terms of the basic trig function. Locate the vertical asymptotes and graph 2 periods. Well, I think 1 period will suffice for the graph. So this just looks almost like a basic tangent function. It's just that b value is 2. So I think it's going to have a different period than a basic tangent function. So the first thing I'm going to do is I'm just going to sketch what a tangent function looks like. I know the tangent function has a point at 0, 0. Well, it's got some asymptotes out here. And I know it's going to be increasing. It's going to look something like this. And then that picture would just keep repeating. The space between the asymptotes would stay constant, and the picture between all the asymptotes would look exactly the same. Excellent. So I just really need to figure out where those asymptotes are. So I know that for tangent, that the period is pi over b. And choose the b value, so my period here is going to be pi over 2. So that means that the distance between the asymptotes has to be pi over 2. So that means this first asymptote is going to be at pi over 4, because that's half of pi over 2 is pi over 4. This asymptote is going to be at x equals negative pi over 4. So that the distance between those asymptotes is pi over 2. So I guess the only difference is that between this tangent graph and the graph of y equals tangent of x, it's just that the graph y equals tangent of x, the period is pi. So it looks like this graph y equals tangent of 2x is repeating more quickly as a shorter period. Excellent. And let's look at question 6. So the equation is y equals negative cotangent of 3x. Same directions. So I'm going to sketch a graph. My axes are kind of slanted here. Of the cotangent function. The cotangent function has an asymptote at x equals 0. It's also going to have an asymptote somewhere out here. I don't know where that is yet. And cotangent, the graph is normally decreasing, but since there's a negative in front of the equation, it's actually going to increase. It's going to look like a tangent graph. I have to figure out the period here. The period is also pi over b. It's going to be pi over 3. So that means that the space between the asymptotes is pi over 3, so if the first asymptote is at x equals 0, this next asymptote would be at x equals pi over 3. So you see, if I wanted to draw multiple periods, it'd be easy, because I could just put an asymptote over here at x equals negative pi over 3, and then I could just put another exact replica of what the graph looks like between the asymptotes, and it would just repeat that way forever and ever and ever on the coordinate plane. So again, this looks like this is a cotangent function, but the negative out in front makes the graph increase instead of decrease, and the 3 just makes the period a third of what the period is of cotangent of x. The period of y equals cotangent of x is pi. The period of my graph in number 6, pi over 3. Excellent. So let's look at number 7. 7's asking us to graph y equals the secant of 3x. Now, in order to graph this, since I'm graphing a secant function, I actually take a moment and I graph y equals cosine of 3x. So I'm going to sketch that graph. So that graph has an amp of 1 in a period of 2 pi over b, which is 3. That answer 1. Okay, so there's one cycle. I'm going to do one cycle on both sides. There's two cycles of the cosine graph. Now here's the thing. I know that the secant graph is just the reciprocal. That the secant function is the reciprocal of the cosine function. So that means if I have a 0 on the cosine function, and I take the reciprocal of that the reciprocal of 0 is undefined. So that means wherever the cosine graph has zeros, the secant graph is going to have asymptotes. And now, look at these max points. That's 1. The reciprocal of 1 is just 1 over 1, so the secant graph would also share that point at 0, 1. But since it's the reciprocal graph, now the secant graph would start opening up, like so. So I'm just polishing off the graph here. So it's like the cosine graph, except where you get the zeros on the cosine graph, that corresponds to asymptotes in the secant graph. And then every max and min corresponds to the same point on the secant graph, but then the increasing, decreasing is kind of flip around. So for example, at 0, 1, I have a point on both graphs. But in the cosine graph, to the right of 0, 1, I start decreasing. Well, I'm going to do the reciprocal of that. I'm going to start increasing in the secant graph. So there we go. I've got, there's my graph for y equals secant of 3x. Now the last problem that I have on here, 23, let's see if I can squeeze it on this page without going to another page. It says, describe the transformations required to obtain the graph of the given from a basic trigonometric graph. So I can actually squeeze in 23 here. So 23 is asking me, if I had the graph y equals cosecant x, and I wanted to transform that into the graph of y equals 3 cosecant x, wants me to describe those transformations, well, I would just vertically stretch the graph, or multiply every y value by a factor of 3. So that's going to be a vertical stretch. And I've finished all those problems. So we'll probably come back and do some more 4 or 5 problems, questions 33, 34, and 36 in the next video.